about chapter 11. So chapter 11, cluster analysis advanced methods. So in face-to-face class, we discussed probability model-based clustering, clustering high-dimensional data, and clustering graphs and network data. So before starting this session, I will ask you some questions to review all the topics covered in face-to-face class. Let's begin with the first question about probability model-based clustering. So in the probability model-based clustering, we discussed together the fuzzy or the soft clustering. The question is why we use fuzzy clustering. Why? Fuzzy or soft clustering. Why we use this clustering? What is the difference between this clustering and all the previous methods of clustering discussed in chapter number 10? So when we talk about clustering, all the methods of clustering are unsupervised, yes. So soft, fuzzy, partitioning methods, hierarchical methods, all this because clustering is unsupervised. But here, why we use fuzzy clustering? We want to class or assign a data object to more than one cluster. Very good. So the object can only be from one cluster. In the previous methods, k-means, for example, or k-midwidth are some methods, and for these methods, one object belongs to one cluster. But here, using fuzzy set or fuzzy cluster, we can define the participation of an object to many clusters. It is clear why we use fuzzy. For example, an e-game could belong to both entertainment and software. In this case, the e-game has a participation to the first cluster and another participation to the second cluster. It is clear? Okay. Let's move now to the second question. Clustering high-dimensional data. So what are the methods used to clustering high-dimensional data? What are the methods or the manners used to clustering high-dimensional data? No. So we have many dimensions. What is the problem for high-dimensional data? Let's begin with the problem. The problem. Yes, dimension reduction is one of the methods used to clustering high-dimensional data. But let's discuss together what is the problem of high-dimensional data. If we have many dimensions, then after that, if we will perform, yes, we have many attributes, and if we will perform the distance between one object and all the centers of our clusters, we will obtain what? We will obtain the same distance. Yes, very good. We talk about the problem of equidistance. So here the distance becomes meaningless. Very good. So there are two methods to resolve the problem of clustering high-dimensional data: the subspace clustering and the dimensionality reduction. Subspace clustering and dimensionality reduction. Okay? So subspace clustering, that means we will search for clusters existing in subspaces of the given high-dimensional data space. And dimensionality reduction, construct a much lower dimensional space and search for clusters there. It is clear? Good. So for subspace clustering, we discussed many methods, many manners. We discussed the bottom-up approaches, the top-down approaches, the correlation-based clustering methods, and the B-clustering methods. And for dimensionality reduction, we discussed the feature selection and extraction and the spectral clustering. It is clear? So now we will move to the third questions: clustering graphs and network data. Can you give me an example of clustering and applications of clustering graphs and network data? An example of or an applications, for example, web search engines, click-through graphs and web graphs, social networks, friendship co-author graphs, yes, customers and products, authors and conferences, etc. So for graphs, we will use a simple distance or a special distance. What is the distance that will be used to calculate the similarity measure? Very good. Geodesic distance. So similarity measure will be created by geodesic distance. And here, what's the meaning of geodesic distance? Geodesic distance is the shortest path between A and B. And if A and B are not connected, in this case, yes, it will be defined as infinite. Also, we discussed the eccentricity of a vertex. Radius is the minimum eccentricity of all vertices, and diameter of a graph is the maximum eccentricity of all vertices. And a peripheral vertex is a vertex that achieves the diameter. So SIMRANK is the abbreviation of similarity based on random walk and structural context. SIMRANK is a structural context similarity based on the similarity of its neighbors. And here in a direct graph we can find individual in neighborhood and individual out. So individual in will be represented by I of V U if U V belongs to E, and for out O of V W if V W belongs to E. Here the order is very important to for in and for out. So for in we begin with the parameter with U, and for out we begin with we end with the parameter in our example is W. So after that we can calculate the similarity with this formula, this mathematical formula, and similarity is based on random walk in a strongly connected compound. Here we can discuss expected distance, expected meeting distance, and expected meeting probability. So for you, just keep in mind that SIMRANK is the abbreviation of similarity based on random walk, and we can calculate this similarity by considering individual in and individual out neighborhood. Graph clustering, sparsed cut. So what's the meaning of sparsed cut? Here we have a graph with some vertices and edges. The cut set of the cut is the set of edges U and V. U belongs to S and V belongs to T. And S and T are in two partitions. So here, for example, the size of cut can be presented as a number of edges in the cut set. Mean cut, for example, here minimum cut is represented by C1 in our example, is not a good partition. So to define a better measure, we can use this sparsity as the size of the cut divided by the minimum of S and T. Sorry. So in our example, a cut is sparsed if its sparsity is not greater than of any other cut. So in our example C2, the cut C2 with the first graph will be A, B, C, D, E, F, L, and the second one will be J, H, I, G, K, is the sparsed cut. For K clusters, the modularity of a clustering assesses the quality of the clustering with the formula Q equals this formula, and the modularity of a clustering of a graph is the difference between the fraction of all edges that fall into individual clusters and the fraction that would do so if the graph vertices were randomly connected. The optimal clustering of graphs maximizes the modularity. So what are the challenges of finding good cuts? High computational costs, so many graph cut problems are computationally expensive, and the sparsed cut problem is NP hard. Need to trade off between efficiency, scalability, and quality. So sophisticated graphs may involve weights and or cycles. The high dimensionality, so a graph can have many vertices, and in a similarity matrix, a vertex is represented as a vector, a row in the matrix, whose dimensionality is the number of vertices in the graph. Sparsity, so a large graph is often sparse, meaning each vertex on average connects to only a small number of other vertices, and a similarity matrix from a large sparse graph can also be sparse. Do you hear me? Okay. So what are the two approaches for graph clustering? There are two approaches for graph clustering. Use generic clustering methods for high-dimensional data. This is the problem of university. Do you hear me? It is clear now? Because I don't know if يعني ممكن مش شبكة. Okay. The second approach designed specifically for clustering graphs. So keep in mind that for graph clustering there are two approaches. The first one use generic clustering methods for high dimensional data, and the second one designed specifically for clustering graphs. So using clustering methods for high dimensional data, for example, we will extract a similarity matrix from a graph using a similarity measure. After that, a generic clustering method can then be applied on the similarity matrix to discover clusters. For example, spectral clustering, approximate optimal graph cut solutions. The second type of the approaches for graph clustering is the method specific to graphs. And in this case, we will search the graph to find well-connected compounds as clusters. For example, scan is a specific method for graph clustering. Scan is the abbreviation of structural clustering algorithm for networks. It is clear. Any questions about graph clustering? Any questions about these approaches? This is a description of scan method. Let's move now to a social network model. Clicks, hubs, and outliers. So individuals in a tied social group or clique know many of the same people regardless of the size of the group. So individuals who are hubs know many people in different groups but belong to no single group. For example, politicians, for example, bridge multiple groups. Individuals who are outliers reside at the margins of the society. For example, know few hermits, know few people, and belong to no group. So the neighborhood of a vertex defined as the immediate neighborhood of a vertex. Like for example here, for our vertex V, the immediate neighborhood are the nodes represented by the yellow. By yellow. This is the presentation of a neighborhood of a vertex. Any questions about social network model? Let's move now to the last point in this chapter, clustering with constraints. So what's the meaning of clustering with constraints? Can you explain me clustering with constraints? Now here in the last example, the yellow here define the immediate neighborhood of a vertex, the set of people that an individual knows. This is an outlier for vertex. The black one can be considered as an outlier. Now, constraints, not outliers. So clustering with constraints, that means we want to make clustering but with some constraints, and these constraints are provided by the user. So for example, me, I want that the object A and the object B must be in the same cluster, and the object C and the object D must be in the different clusters. This is the meaning of a constraint. It is clear? So why constraint-based cluster analysis? Need user feedback. So users know their applications the best. Less parameters, but more user-desired constraints. So here the user provides some constraints, and we want to make clustering according to these constraints. In ATM, for example, in ATM allocation problem, there are some obstacles and desired clusters. Here we talk about constraints. Categorization of constraints. So the constraints can be categorized on instances, on clusters, on similarity measures. 3 categories. Do you hear me? Are you here? Do you hear me? Do you hear me? Okay. I will repeat. So there are 3 categories of constraints. Constraints on instances, constraints on clusters, and constraints on similarity measurement. Okay? 3 types or 3 categories. Let's begin with the first category. Constraints of instances specifies how a pair of or a set of instances should be grouped in the cluster analysis. It is clear? For example, must link versus cannot link constraints. So what's the meaning of must link X, Y? That means X and Y should be grouped into one cluster. This is the constraint. X and Y should be grouped in one cluster. And constraints can be defined using variables. Cannot link X and Y if the distance between X and Y more than D. So it is clear the first category of constraints on instances. Good. The second category is constraints on clusters. Specifies a requirement of the clusters. For example, we specify the minimum number of objects in a cluster, the maximum diameter of a cluster, the shape of a cluster, for example, a convex, the number of clusters, for example, K and K means, etc. So the second type of constraints is a constraints on clusters. The third type of constraints is constraints on similarity measurements. It specifies a requirement that the similarity calculation must respect. For example, driving on roads, obstacles, etc. So there are some issues. For example, hard versus soft constraints. conflicting or redundant constraints, etc. Any questions about all these constraints? Constraint-based clustering methods handling hard constraints. Now we'll talk about hard constraints, how we can resolve the problem of hard constraints. Like filtering here, this is some rules provided by the users. Okay, so the user say, for example, all the students of SU must be in the same cluster. This is a constraint. Or when we make a clustering, there are some obstacles. We cannot make clustering. يعني ما بنقدر أن نعمل clustering فوق الobstacle هذا. So example of a method that resolves hard constraints, the COPK means algorithm. So this algorithm generates super instances for masking constraints. Here, the idea of this algorithm, if we have a masking constraint, masking, that means two objects must be linked in the same cluster. In this case, we will generate super instances. Super instances that in this instance we can find all the objects that must be linked. After that, compute the transitive closure of the masking constraints to represent such a subset. Replace all those objects in the subset by the mean, and the super instance also carries a weight, which is the number of objects it represents. Another manner, conduct modified k-means clustering to respect cannot link constraints. This is another manner to modify k-means to resolve a hard constraint like cannot link. So cannot link, that means we cannot find x and y together in the same cluster. In this case, we will modify the center assignment process in k-means to a nearest feasible center assignment, and an object is assigned to the nearest center so that the assignment respects all cannot link constraints. So here in this slide, we see together how we can modify the algorithm, the basic algorithm k-means, to handle hard constraints. It is clear? Any questions about this slide? Another type of constraints is a soft constraints. So treated as an optimization problem, when a clustering violates a soft constraint, a penalty is imposed on the clustering. Overall objective, optimizing the clustering quality and minimizing the constraint violation penalty. For example, CVKE, the abbreviation of Constraint Vector Quantization Error algorithms, conduct k-means clustering while enforcing constraint violation penalties. Here, for soft constraint, for example, we will consider the problem of masked link, and when there is a violation of this constraint, we make a penalty. So penalty on a masked link violation if objects x and y must be linked, but they are assigned to two different centers, C1 and C2. The distance between C1 and C2 is added to the objective function as the penalty. A second example, penalty of a cannot link violation. Here, if the objects X and Y cannot be linked, but they are assigned to a common center C, we will calculate distance between C and C prime, and this distance will be added to the objective function as the penalty. In this case, C prime, in our example, C prime is the closest cluster to C that can accommodate X or Y. So for you, here we discussed two types of class of constraints, or two manners to resolve the problem of constraints. The first one, we will consider the constraint as a hard one. For this case, we can use the K-means algorithms, or we can modify K-means by the modification of the center assignment process. The second is we will resolve constraints, but by another manner. We talk about soft constraints. Here we will use penalty concept, and we will define a penalty for a must link violation and penalty for a cannot link violation. It is clear? Any questions about handling hard constraints and handling soft constraints? Okay. So this is an example clustering with obstacle objects. Here the constraint is obstacle objects. Okay. The obstacle objects are defined by the blue line, and we want to create clusters and to take into account the constraint of these obstacles. Okay, and the first figure here in the left, not taking obstacles into account. The second one in the right, taking obstacles into account. So we can see the difference between the first result and the second result. It is clear? User-guided clustering, a special kind of constraints. So here we discuss together a special kind of constraints, the user-guided clustering. So user usually has a goal of clustering students by research area, for example. In this case, user specifies his clustering goal to cross clustering. In our example, the user hint is the area of the research. So user specified features in the form of attribute, and this feature is used as a hint, not class labels. So the attribute may contain too many or too few distinctive values. For example, a user may want to cluster students into 20 clusters instead of 3. Additional features need to be included in cluster analysis. Comparing with semi-supervised clustering. So semi-supervised clustering, user provides a training set consisting of similar must link and dissimilar cannot link pairs of objects. And user-guided clustering, the user specifies an attribute as a hint, and more relevant features are found for clustering. This is a comparison between semi-supervised clustering and user-guided clustering. Why not semi-supervised clustering? So much information and multiple relations is needed to judge whether two tuples are similar, and a user may not be able to provide a good training set. It is much easier for a user to specify an attribute as a hint, such as a student research area. So the conclusion is, if we use a user-guided clustering, it is more easier to create our clustering with this special kind of constraint than using a semi-supervised clustering. So in this chapter, we discussed probability model-based clustering, fuzzy clustering, probability model-based clustering, and the EM algorithms. All these types provide the possibility of an object to belong to more than one cluster. We discussed also methods for clustering high-dimensional data, the subspace clustering, and the dimensionality reduction. An example of the subspace clustering, the big clustering methods, and an example of dimensionality reduction, the spectral clustering. Clustering graphs and networks and network data is also discussed in this chapter. We discussed graph clustering, the mean cut versus the sparse set cut, the high-dimensional clustering methods, and graph-specific clustering methods. Clustering with constraints. So constraints can be on instances. Also, the constraints can be on clustering. Constraints can be on distance and measurement. We see together the must link constraint and the cannot link constraint, etc. This is the last slide of this chapter. Any questions about this chapter? So if you don't have any questions,